Thank you. I'd like to thank the organizers for giving me this opportunity to present this talk at this workshop. And I will present this topic and this work on behalf of the HOPE collaboration. I'll introduce my collaborators in a bit. And so just for the references of this, of the materials presented in this talk, the story actually goes back to a very old paper written by Will Demotte and myself back in 2006. And in recent years, we picked up this idea presented in this paper again and made some progress in deriving more analytic results and also to perform a numerical test of the method. So what I'm presenting today will be mostly based upon these few articles listed here. And the work has been done with this HOPE collaboration. HOPE stands for heavy-quark operator product expansion, which is actually the method we're using, and I'll explain it in this talk. And these are my collaborators, including Isaku Kanamori, who is sitting in the audience. And I want to mention that this work has actually been mostly done by these two young colleagues, Anthony Grebe and Robert Perry. They are the people who actually did most of the hard work for this project. Okay. So in this talk, I will first go through some general issues in tackling particle physics from the Euclidean space formulation of Lattice QCD. This is actually a very well-known problem, but I think maybe not everybody in the audience is working on particle physics. So I will just remind you briefly what's happening there. And then I will introduce the HOPE method, and I'll use the Pion light-cone distribution amplitude as an illustration how this can be implemented. And I'll show you numerical results of the second moment of this light-cone distribution amplitude. And I'll also tell you what's going on in our pursuit of some higher moments of this distribution amplitude. And I'll tell you where this project is going and conclude. Okay, so let's start from the general issue in lattice calculations of particle physics. And we know that particle physics actually comes from the study of the deeply inelastic scattering, as indicated here. And you know that the cross-section can be written as the imaginary part of this full amplitude using the optical theorem. And you want to know the imaginary part of this amplitude, and you know that it's actually very difficult in Euclidean space. So that's difficulty number one. What you can do is that if you do PQCD study, you can show that the imaginary part of this amplitude can be written using a factorization theorem into this form with these twist-2 contributions, okay, where this H is just the hard scattering kernel that can be computed perturbatively, and this F is just the particle distribution function. Now, this particle distribution function, though, is defined with the matrix elements of nucleon states, where S is the spin, sandwiching this Wilson line going in a light-cone direction. This W is just the Wilson line. This gamma, big gamma, is the appropriate Dirac matrix structure that gives you the correct matrix elements. Okay, so then if you write down things this way, then you have to actually tackle non-perturbative QCD dynamics on the light cone. And you know that it's also very challenging in Euclidean space, because in Euclidean space, the light cone is just one point. So being faced with these kind of difficulties, traditionally, what's happening on the lattice was that people would just rely on light cone operator product expansion, okay, and they would just write this light cone direction Wilson line in terms of a tower of local operators, and they keep the twist-2 contributions, and that would just give you the Melly moments. Okay, and the twist is defined as the difference between the dimension and the spin of the operator. So this is what's happening, what was happening before. Okay, and I'm just listing the results of this Lycon OPE here, that you have two currents, and you take the twist-2 contributions, and you can see that these operators are organized this way, that you have more and more derivatives, which will give you higher and higher dimensional operators here. And they're all twist-2 because these Lorentz indices will give you more spins as well. Okay, so in principle, if you can actually compute many matrix elements of many of these operators, you can hope to be able to reconstruct Pion distribution functions, because in the end, they have to give you, if you know infinite number of them, they should actually give you the DIS, right? But you see that on the lattice, you break the rotation symmetry, and therefore spin is no longer a good quantum number. In other words, if you consider these operators with different spins, they will mix under renormalization. And if you want to get twist-2 contributions, then that means operators with different dimensions will mix. And what's even worse is that higher dimensional operators will start mixing with lower dimensional operators. Okay, so because of this difficulty, lattice calculations through this conventional method were actually being restricted to extract only for the first few moments for Pion physics. And in Pion distribution functions, it's often just taking you to the third moment. And for the Lycon distributions, often you can only get the second moment, which is the first non-trivial Mealy moments that you will get, or that you want. Okay, so since this is a renormalization problem, right? Because you see, this kind of operator mixing actually comes from the fact that you are writing this Wilson line in terms of all these local operators, and that gives you more structures in your UV divergence. And so a very natural way of solving this problem is to try not to compute matrix elements of local operators. Instead, if you can try to compute some non-local operator matrix elements and try to connect this kind of matrix elements to the matrix elements you want, maybe through some perturbation theory, then you can actually go beyond the status of having only information from the first few Mealy moments. And that's the idea behind many so-called novel approaches in this field. Okay, so generically, I'll reiterate here that we don't want to compute these local matrix elements to extract Mealy moments again. We want to try to compute matrix elements of some non-local objects. And these non-local objects are typically unphysical, because you know that if you want the physical matrix elements directly, you have to compute matrix elements of this Wilson line going in the Lycon direction, and that's just not feasible directly on the lattice. So you want to do some, you want to get some matrix elements of non-local and unphysical objects, and then you try to reconstruct the Lycon Pion distribution function through some perturbative matching kernel or whatever you can get analytically. So, I mean, there's this very famous approach proposed by Shandong Ji in recent years under the name of quasi-PDF. Of course, he proposed that you can actually compute the matrix elements of a space-like Wilson line, and he managed to derive matching conditions to reconstruct this Lycon distribution function, for instance. And the variance of this quasi-PDF is going under the name of pseudo-PDF, which will, these two approaches have been heavily pursued in recent years. But there are also other proposals, like back in 2008, Brown and Miller also proposed this idea of computing matrix elements of two local currents, and they're separated with space-like distance, so nothing can go onshore here. You can't cut this diagram, so that's unphysical. And they claim, and they worked out that this method could actually be used to obtain higher Mealy moments in this Pion physics. And there are also many other proposals, but today I will just concentrate on the proposal Demot and myself put forward about 15 or 17 years ago. Our proposal is that we want to compute two flavor-changing currents here and here, and the current would actually couple to, say, your physical light quark to a heavy quark that is not in the action, is completely valence, in a sense that it's quenched, okay? But it's propagating. We call it heavy quark just because it carries a heavy mass, but it's fully relativistic, it's propagating, and therefore it's only allowed to propagate between these two currents because it's valence. It can't go into the sea, so it can't go into a hadronic state. And so this actually makes it easy to do the OPE, and then we actually show that from this OPE, you can try to fit these higher Mealy moments out of out of the formula that you can derive. And I'll show you an example by presenting you the calculations for the Pion-Lycon distribution function. Okay, so then let's go on to introduce how to implement this whole method and what it really is by looking at this example of Pion-Lycon distribution amplitude. But before I proceed, let me remind you what Pion-Lycon distribution amplitude is and why it's important and why it's interesting, at least, to study it. Okay, so the Pion-Lycon distribution amplitude is denoted by this phi sub pi here on this slide, and C is actually parameterizing the fraction of Pion momentum, say, carried by one of the valence quarks. Okay, and of course, then 1 minus C is the fraction of momentum carried by antiquark. And mu is the renormalization scale, okay, and F pi is just Pion decay constant, of course. And on the left-hand side of this formula, you have this matrix element of a pion going to vacuum, sandwiching this operator with a Wilson line, W here going from minus Z to Z, and this should be also the Lycon direction. Okay? And you can show that in the UV regime, the QCD actually possesses an approximate conformal symmetry, and if you use that symmetry and to guide an OPE, you can actually write this Lycon distribution amplitude in this form, okay, where this C sub n 3 over 2 are just a bunch of Gegenbar polynomials. They actually emerge naturally from the OPE. And these phi sub n are just the so-called Gegenbar moments in this formula. And these are non-perturbative objects. So if you can actually compute these Gegenbar moments, then you can try to reconstruct these Pion-Lycon distribution amplitudes. But the good thing about this formula or this OPE is that you can also try to get the renormalization group running properties of all these Gegenbar moments, okay? And they don't mix under RG running at one loop. And so at one loop, you can show that if you actually run to very high scale, it's dominated by just the leading Gegenbar moments. And this is just from the results of the enormous dimension, one loop enormous dimension that you can compute in perturbation theory. So the RG evolution actually tells you that the RG evolution convoluted with this, the results of this Gegenbar OPE would just tell you that when the renormalization scale is very high, this Lycon distribution amplitude would just take this asymptotic form, because these guys will all just vanish, or all just vanish when n is not 0. Okay, they're suppressed, highly suppressed by the RG running. But how high exactly is this happening? How high of the scale is this happening? Is not known. Okay, we just know that when this goes to infinity, this has to happen. Okay, so you know the asymptotic shape of this distribution amplitude. It has to be like this. Okay, so now the task is we want to know how far away this guy is really deviating from this asymptotic form at finite mu, of course, right? So how do you do it? You look at the left-hand side of this formula, and you do an OPE, a Lycon OPE to this operator here with a Wilson line connecting two quarks, or a quark and anti-quark. And as usual, this will just give you a tower of operators. Well, these are just twist 2 results. Of course, you have higher twist contributions as well. And these local operators, as usual, will just give you the Melly moments of this Lycon distribution amplitude. This you can show. So by matching up these two sides, you can actually derive relationship between the Melly moments and the Gegenbaur moments. And I'm listing the first few of them here. So this is to tell you that you know these Melly moments, and then you can reconstruct these Gegenbaur moments, and then you can try to reconstruct this guy. Okay? So you see that if the second moment is very small, okay, I mean as small as 0.2, then it still largely looks like the asymptotic behavior. But then if c squared, the second moment, becomes a little bit bigger, 0.25, you see that this twin peak shape starts to appear. And mind you that these are actually the typical values lattice results get these days. Okay, and lattice results on the second moment actually typically will give you that values between 0.2 and 0.3. Okay, so you see that this can actually greatly affect the shape of the momentum distribution inside a pion. Yeah. Okay. Now, and also by the way, I mean the reason why I'm not listing C4 is just that lattice calculations. I mean the reliable lattice calculations these days just stopped at the second moment because the power divergence I mentioned earlier on already shows up in lattice calculation for this C square, and you already have to use all sorts of tricks to subtract these power divergences, and these tricks will not work if you want to go beyond the second moment. Okay. Now, a bit of phenomenology. So why is the Pion distribution amplitude interesting? Okay, I mean, say for example, if you look at the Pion form factor, which is actually very important for us to understand the exclusive QCD processes. Okay, you can actually factorize this Pion form factor in this way, where this TH is just perturbative kernel that you can compute in perturbation theory, and is convoluted with two Pion-Lycon wave function like this, as pictorially represented here. Okay, and a very large Q square, this can actually take the asymptotic form as listed here. So you could input this Pion-Lycon distribution amplitude and see what happens. But without such information, what you can do is that, without non-perturbative inputs, what you can do is just to put in the asymptotic form of this phi pi and see what happens. And this is the status. You see that the asymptotic behavior of the Pion-Lycon distribution amplitude will give you the prediction of the form factor here. And these are the experimental results, the latest experimental results. And this curve is a model calculation from the vector meson dominance. And this is the Schwinger-Dyson equation calculation with the modeling, which appeared like 10 years ago. So clearly, the data is indicating that at least Q square, this range of Q square is very far away from asymptotic form. Okay, so it's actually very important to have results, to have more precise results for this Pion-Lycon distribution amplitude to try to understand this. And also for people who are interested in flavor physics, this Pion-Lycon distribution amplitude is a very important input for understanding, for example, the theoretical predictions for the B to pi pi decays. Okay, but you can factorize again into these meson-Lycon distribution amplitudes convoluted with a PQCD kernel that you can compute analytically. Okay, So enough phenomenology. So how are we going to get this Lycombe distribution amplitude or its higher moments from our hope method? So what we study is the following. We study the starting point is this matrix element. Okay, so this is Pion going to vacuum, which is the insertion of this time order product of two axial vector currents. Okay, separated in some spatial, some Euclidean distance. Okay, so it's pictorially drawn here, and this capital psi now, as indicated by this blue line here in this diagram, is our valence fictitious but relativistic propagating heavy-quark. Okay, and we also take the anti-symmetrization of the Lorentz indices of these two currents. Okay, so if you look at this matrix element with this anti-symmetrization, and you do an operator product expansion, okay, to treat these two currents, this is the result that you get. Let me explain a little bit because this is an important formula. And so this, again, is the hadronic amplitude that I showed on the previous slide. And this is the Levi-Civita tensor that comes just from the anti-symmetrization of your Lorentz indices. And PQ, of course, P is the momentum carried by the pion, and Q is the injected momentum at the operators or at the currents. And these theta and eta are just kinematic variables that emerges in your calculation, in your tree-level OPE calculation, and they are listed here. And this Q twiddle will just emerge naturally as well. Okay, and notice that here the heavy-quark mass appears. Okay, so these in these quantities in dark blue. Oh, and by the way, this Gegenbaur polynomial here are just the effects of the resummation of the target mass effects. Okay, if you don't do it, then it's just one. Now, all these quantities in dark blue or in blue can be obtained through a tree-level calculation. That's very easy. Just do the OPE at tree level. And this CW in cyan is the Wilson coefficients that will actually involve a more complicated one-loop calculation, but you can do it as well. Okay, and the idea is that these hadronic amplitudes can be computed numerically on a lattice, and all these things you can do analytically, and then the hope is that you can actually try to fit these moments out from this OPE formula. In particular, if you actually work in the continuum limit, then there's no funny divergences coming up at all. Okay, and then of course, these results here are just from the twist 2 contributions, and in this OPE, it's clear that you will have higher twist contributions that emerge as well, and they go like 1 over Q twiddle to the power of 3. And I'd like to mention that you have a heavy quark mass, and on the lattice, you can only input your bare heavy quark mass. Of course, you can actually do a complicated job by determining this heavy quark mass, by computing these heavy quark masses in the renormalization scheme that you are interested in working with. Often it's the MS bar scheme, because that's where we compute our Wilson coefficients of one loop. But on the other hand, you can actually also leave it as a fit parameter, and you can just determine it from your data. Okay, and that would just require some tuning as well, of course. But in any case, it requires some tuning to determine this heavy quark mass. Okay, so in this approach, at the first sight, it looks like something very reasonable. Once you have data from lattice calculation, once you have this formula, you can just fit. But in practice, it's actually not as easy, because if you look at this guy here, this is actually, again, the quantity that I mentioned that you could obtain through your through your tree-level OPE. So let me explain this plot a little bit. So again, this plot is actually prepared with these parameters that we put in. But the gist of this plot is that if you look at the OPE results, And you see that this quantity, which I denote as Wn, is actually taking such hierarchy of values when you go to different n. N just labels the nth moment in this OPE result. And you see it highly depends on what kind of momentum carried by the pion. So, but the general trend is that if the pion carries very low momentum, the extreme cases that is at rest, you see the higher moments can be highly suppressed by this kinematic factor that you obtain in your OPE result. And you really have to boost up your pion to enhance the sensitivity to higher moments here. So like, for example, if you take the fourth moment, if you want to determine it using data with pion at rest, it's really hopeless because the signal will be really small compared to the zeroth moment, which is just the normalization. But if you can boost up to this momentum, for example, you have actually good hope that you can get something out of your data. So that's the gist of this plot. And this I probably don't have time to explain, but I'm just flashing it to tell you that this is exactly what we understood by doing some detailed study of the convergence property of the OPE as well. Okay, now let me then jump straight to a little bit more details about the calculations. So again, we are trying to get the higher moments. As I already showed on the previous slide, those higher moments contributions are actually suppressed compared to lower moments. So let's look at, any possibility of enhancing the dependence on these higher moments. And we found actually a trick to do so. So let's look at the Lycon distribution amplitude. Okay, this is the matrix elements you can compute on the lattice, and these are the results. And let's take the Lorentz indices to be in the x and y direction, and the Levi-Civitas tensor will give you this. And then the injected momentum at the operator and the pion momentum will take this form here. And you can play with the trick that by noticing that you're in Euclidean space in such a way that the force component of the pion momentum is just I times its energy. So it's purely imaginary. And so if you make this choice, okay, then this formula is reduced to this. So you have a purely imaginary factor in front of you. And then you know that these Wilson coefficients are real. On the other hand, because of the kinematic factor combination here, accompanying the second moment, this guy is complex. So if you look at the imaginary part of this hadronic tensor, the OPE formula tells you that it starts from the zeroth moment, which is just normalization that you're not interested in. But then if you look at this matrix element and you study its real part, then it actually starts from the second moment. Okay, so the leading contribution to the real part of this guy will become the second moment if you choose this kinematic combination. So this is what we did in our numerical work. One more word about the approach is that what I've been presenting to you is actually completely done in momentum space. And with a lot of people, we know that it's often more convenient to work in time momentum representation, which just means that you do the Fourier transform of the force direction here. So this is a typo. This should be dq4. Okay. So this, instead of having q4, you have the Euclidean time dependence in this guy. So this is a typical time momentum representation for lattice correlators or matrix elements. But then, of course, if you work with this TMR approach, you have to do the Fourier transform of your Wilson coefficients because those things are often computed completely in momentum space. Okay, but this you can do. And we actually found that for reasons I can explain maybe offline, that this time momentum representation approach tends to give us smaller systematic errors. So for the results I'm presenting in the next 10 minutes or so, they will actually be obtained completely in this method. Okay. Okay. So first, let me present you a feasibility study because this is actually something new, although it was proposed a long time ago, and it was never really studied in detail, in particular for numerical test. So for our first proof of principle calculation, we actually did it with a bunch of quench ensembles at this unphysical Pion mass, and we have 4 ensembles with 4 lattice spacings in this range. And the volume, the physical volume is fixed to be around 2 Fermi. And so the purpose of this is to see if we can actually get reasonable results for, say, the second moment, just to prove that we can do it first. Okay? And in the procedure, we are trying to learn how to control the errors as well. And it turns out that we get pretty good results for the second moment, which I will show you. And I will also show you that we've been doing this, the force moment calculations, and so far, exploratory result looks actually quite reasonable as well. And what I will also mention is that these exploratory calculations can be done completely on a medium-sized cluster that you can house on your campus. And we've been doing this on a 60-node Intel kernel cluster. It's a medium-sized thing. Okay, so first of all, let's look at the result of the second moment. So this is a table of details of our lattices, okay, and with the number of configurations and the number of sources that we invert on each configuration. And this is a list of the heavy-quark masses, okay, that we have. This is 1 over m psi in GeV, these things that we tune. And this is just to go across different lattices. For example, for this m psi, we tuned it on the four lattices we have, and so on and so on. And then, of course, here, if you go down, it gets heavier, okay? And it's harder to have lattice artifacts in control, especially on the coarse lattices, okay? And then we actually place cuts in this range to study the systematic effects in our calculations. Okay, we cut away some data points which, we believe that the lattice artifacts can be very challenging to control. Okay, and also for this second moment calculation, we work with such momentum injection. Okay, in units of your lattice momentum. And I also like to mention in passing that although we are using the Wilson plaquette and non-perturbatively improved Clover action, we don't improve the operators because you can actually show, as we actually demonstrated in one of our recent papers, that this hadronic tensor is automatically order improved without improving the currents. Okay, so our continuum extrapolations can be done with order A² corrections. Okay, so the correlator we compute is of this kind, that you have a Pion source here, say at the origin, and that it propagates, and you hit it with two heavy light currents, with this thick line representing the fictitious heavy-quark in our approach. And you can study this as 3-point function to show that this actually gives you this Hope hadronic amplitude time momentum representation times this quantities that you can fit from your 2-point function. Okay, so this is a typical manipulation that lattice people do. But the question is that here we have a Pion state propagating to, say, this point, this tau e point, and we would like to have the excited state contamination under control, and that we did study. Okay, and this is just done at 2 different tau. Tau is just the time appearing in this matrix elements, which you can show to be just the difference between the time slices where you insert these 2 currents. And you see that indeed this the first current will have to be inserted at late enough time in order to have the excited state contamination under control. Okay, So this is what we did. And so once we check that the excited state contamination is under control, we get our data points, and we can do a fit. Okay, so these are just fits to the OPE results, and we work in a time momentum representation, so we are just changing this tau in our OPE formula instead of Q Twiddle square. And so these are the results of the fit of the real part, imaginary part. Again, as I said, for the imaginary part, you can determine this F pi, and we also fit our heavy quark mass from the imaginary part. And from this real part, it's more sensitive to, the leading sensitivity is to C square, and that's where we determine this C square. And if you do that, then these are the results you get at various heavy quark masses that we do our simulations, and at 4 different lattice spacings. And then what you want is, of course, to extrapolate to the continuum limit. And also, the OPE formula would actually be subjected to higher twist corrections. So you want to extrapolate away this higher twist contamination, which should go like 1 over m psi in this quantity. So this is the formula that we use to do this simultaneous extrapolation to the twist to limit and the continuum limit, where we mimic the lattice artifacts here, and also the higher twist effects here. And so this C square is the extrapolated results as indicated here. So to compare with previous calculations, I have a plot here. Okay, so these are actually some recent previous determination of this quantity. And our results are listed here. You can see that the TMR analysis gives us smaller systematic effects. Okay, and here's the list of the systematic errors that we estimated, and you can see that the dominating error comes from the higher twist effects. And of course, to reduce this, what you need is to have a heavy quark mass, and to do that, of course, again, you need final lattice spacing beta as well. Okay, but since this is a proof of concept calculation, it's actually pretty nice to be able to extract this C square in a quench calculation to this kind of precision. So we're very happy. And then the next step is to go beyond this, and I only have like 2 minutes left. So I will just go very quickly on this. And this is completely exploratory. This is a much harder calculation. And it's much harder because, first of all, we have to use the simulations with a larger pion momentum, and we do it with these 2 lattice units. And because of that, of course, you have bigger excited state contaminations, and you have larger statistical errors. So we use momentum smearing for the Pion interpolating operators, and we also do GVP studies for our interpolating operators as well. We did all we could to try to enhance the signal. And so far, we've done simulations for this coarser lattice spacings. And this one, I think we already have about 2,000 configurations. Okay, and the 48 cube lattice we haven't started doing yet. So now, so without going into details, I'll just flash you what we have so far. I mean, the procedure of getting this C4 is very similar. You just have to fit to your OPE formula. And you see that, first of all, by using this higher momentum data, we also checked that we could get the second moment. And indeed, these are the points of our second moment without extrapolating to the continuum limit, of course, and with different, and also without extrapolating to the twist to limit. And the gray bands are representing the errors of our previous calculation, meaning the results of C square from the Hope method that just presented to you 3 minutes ago. And you see that's how we get consistent results with ourselves, which is pretty good. So this is a sanity check. And then this is our result of C4 at 2 lattice spacings with various heavy quark masses. And there's a very recent determination of C4 coming from the Brookhaven group at single lattice spacing, and it's here. By comparing with their results, it looks like, I mean, this is their lattice spacing. So by comparing with their result, it looks like we're actually getting something also, not crazy. And also, as expected, this force moment should be smaller than the second moment, because it's higher Mealy moments. You have more powers of C in the extraction of the moments. So this is a work in progress. We'll just add more data points here, and we'll also reduce the errors on these points as well. So with that, I will start my conclusion. I mean, the first thing is that I introduced in this talk this Hope method, which is not very new already, but nevertheless, the detailed study of this method is new, and we numerically tested this method by computing the second moment of the light-cone distribution amplitude and show that it actually works well. And we are also getting very reasonable exploratory results for the force moments, and this will be something new, and the goal is to get this in the continuum limit in a quench approximation first in the following year also. And in the meantime, we also have plans on applying the same method to other parton physics quantities. Okay? And another thing is that although the strategy we are after is mainly for obtaining the higher Mealy moments of these partonic quantities, we also showed in one of our recent papers that the Hope method could also be used to get directly the x-dependence of these parton distribution functions and light-cone distribution amplitudes, a bit similar like what a quasi-PDF approach. Okay, so this is also on our agenda list that in the future, with the available capacity, we may actually try this direction as well. And also, my last slide just shows that we are actually starting to do a calculation to pursue precision prediction for the light-cone distribution amplitude of Pion. For this, of course, I mean, this you can no longer done at a small or medium-sized cluster. So we'll be using the CLS ensembles granted to us, and also we are going to do this calculation on the Fukaku machine here. So that's it. Thank you.